It's not changing that much. Still reading about 300. It'll obviously get higher directly under the bulbs. So, yeah, 900. Maybe raise it up a bit. 600 directly under a single bulb. 400 in the middle between bulbs. 130 in the back corner there. It'll do for now. We'll try this. Probably hang it higher with the caps off. But we'll try this for now and just do a little power map. So we're going to take our readings for this fixture. First of all, it's consumed watts. So 6 by 13 is 78, so exactly that, 78.5 consumed watts from the 6 bulbs, so that's perfect. Let's write that down. So 6 by 13 watt Phillips. 2700K. 78.5 watts consumed. Let's see what the hanging height is. So it's 8 centimeters or 3 inches. So 8 centimeters, and then we're going to, you can see here there's 2 foot by 2 foot or 60 by 60 centimeters, and then in each foot square we're taking 4 measurements, so basically it's 4 measurements by 4 measurements. I'm going to draw that here. So we're going to close up the doors, switch off the other lights, and test this now. Just take a few minutes. Minus 16, 289. And so 289 micromoles per meter square per second average over 0.6 meters by 0.6 meters is 0.36 meters squared. So 289, average power 289 multiplied by the area is 104 micromoles. That's being output onto that 2 foot by 2 foot area. And 104 divided by 78.5 watts. It equals a 1.32 micromoles per watt efficiency. So let's run through that again. 78.5 watts consumed. Here's the power map. Add all them together, divide them by 16. So 4630 divided by 16 is 289 micromoles average. 0.6 by 0.6 meters squared is 0.36 meters squared. And you get 104 micromoles by multiplying the average micromoles by the area. and then divide the number of micromoles by the consumed watts, and that gives you the efficiency, 1.32 micromoles per watt. So yeah, not bad at all. Now for the big one, which is to take the tops off the lamps, and see does removing the diffusion covers improve that efficiency. So let's go and do that. Okay, so there's a element of danger here. First of all, these are running quite hot. I've been running for a while, but I'm gonna have to get in here and cut these off. These covers. So good result. So again, 6x13 watt Philips, 2700K color temperature. No diffusers taken off. 81.2 watts consumed. It's 11 centimeters from the top of the sensor to the underside of the cutoff bulb. Here's the power map. Add them all together. 6450 divided by 16 is 403 micromoles per meter square per second average. By the area, 0.36, so it's 145 micromoles per second coming onto this area. 145 divided by 81.2 watts is a 1.78 micromoles per watt efficiency. So yeah, there you go. So that average of 403 micromoles in a 2x2 is perfectly good for growing. And of course, all you need to do is add on extra bulbs. You look at this fixture here. There's plenty of room. You could have 9 or 12 bulbs in there if you wanted to. You could go up to 800 micromoles per meter square per second with 12 bulbs. Downsides. So wiring is exposed up here. You could pour acrylic or resin in there, seal them up. You could cover this whole thing in plastic. The LEDs are exposed, but it doesn't really matter. You don't have to worry about that too much. There's only low voltage on this side. Biggest one is probably electrical. Again, it doesn't really matter for the consumer. So we'll have a look here. You can see this, but 225 volts, 0.6 amps in this cell. Power factor there, 0.57, 0.57 power factor. Now that doesn't really matter for the domestic person. Power factor is complicated to explain, but basically means your electricity supply is not synced well. Or these devices, the way they consume the power is not synced well with your electricity supply. And in commercial premises, you get punished for that because they measure power factor. Domestic, I don't think they do, so it doesn't really matter. So yeah, it's nice, cheap, easy, efficient, reasonably safe DIY grow light. Hope you enjoy.